So thanks very much for the invitation to be here. So I've been asked to talk about black hole accretion disk Coronae, and of course, the theme of this session are pair plasmas. So I'll be sort of stressing the role of pairs here. My goal here is actually to have a genuine review of this area, and try to have it be a good introduction for the non-astro people here, the laser folks here. And as well as bringing up what I think, my favorite list of some interesting recent topics, a lot of which are coming from the observational side more than the theoretical side, and I don't mean that as a disrespect for my theoretical colleagues here. It's a huge literature on this topic, going back into the 1970s, so I apologize if I haven't given references to people who have done a lot of great work in here, many of which are here. Okay, so let's jump straight in. A fundamental fact of accreting black holes is they emit X-rays. And if you just point the Chandra X-ray Observatory, which is our premier sensitive X-ray observatory, at a blank patch of sky, you see this bunch of stars. They're not stars. Every object here is an accreting supermassive black hole, so it's an active galaxy, AGN. And in the AGN world, we very much think of X-rays as one of the primary ways you can go out and discover these objects. And some of us are spending time trying to build the future machines that will do this at high redshift. So it's X-ray emission from black holes, both stellar mass and supermassive, is a very fundamental aspect of black holes. Yet it is surprising they emit X-rays at all. And just to see that, to sort of go to some of the simplest ideas of accretion, the fundamental power source is of course accretion of matter onto the black hole. And if you just imagine taking a blob of the inflowing matter and moving it in, you're simply releasing its gravitational potential energy. And there's a conveyor belt. There's a continuous mass accretion rate coming into here. There's an m dot moving in. If you simply take this energy and assume it's locally dissipated and radiated as a black body, these accretion disks are often considered to be optically thick, then you can very easily just write down a formula for the effective temperature of the material that's falling in. One extra little step you can do is recognize this is actually in a rotationally supported disk. There's viscous transport of energy that goes on through the flow, so you get some modifications in here, even with fairly light touch fluid dynamics arguments. But still, you can write down a fairly simple form for what the temperature of this disk should be. You plug numbers in for reasonable accretion rates, and what do you get? For accreting stellar mass black holes, you get effective temperatures of 10 to the 7 Kelvin. Fine, that's an X-ray source, soft X-rays, admittedly. For active galaxies, you get 10 to the 5 Kelvin. That's a UV emitter. That's not an X-ray emitter. So the very fact that these objects, that the supermassive black holes are emitting X-rays is a surprise from the outset. Now, of course, from the title of this my talk, you know what the answer is. There's another object we know, which is fundamentally cold, but emits X-rays. That's the sun. And we know that happens in a hot, magnetically powered corona. This is a gorgeous image of the solar corona with NuSTAR, one of the very few X-ray telescopes you can actually point at the sun. Or they let you point at the sun. So that's the picture we have here. Now, in the sun, the solar corona, there's a very small fraction of the total bolometric energy that comes out in the X-rays. It's something like 1 part in a million comes out in the solar corona. One fundamental difference with black hole coronae is that fraction is much, much larger. So these coronae are much more of an important, energetically important component of the system. So this is a spectrum of, one particular fairly representative object, and you can see here all the way from infrared through optical into the X-ray band, the spectrum here. This broad bump here that you can see in the optical is mostly the thermal emission from the accretion disk. Lots of emission lines on there because it's a messy area. There's lots of interesting reprocessing that goes on. But fundamentally, we believe you're seeing the thermal emission from the accretion disk, the thing that I highlighted just earlier. But then you've got this extended tail on the spectrum. This is the emission from the corona of the black hole, and there can be 10% or more of the total bolometric energy can be in this tail. So energetically important. And as we'll see in a minute, there could be that a much larger fraction of the energy is actually released in the corona, and then some of it just shines back down on the disk and heats the disk up, giving you this emission there. Okay, so let's quickly address some of the basic physical processes that are at play. So accretion is fundamentally a magnetic phenomenon. We've known that now for 30 plus years. That, and there goes the movie froze again. We've known that for 30 plus years that even in fairly vanilla accretion disk models, the fundamental process that's giving angular momentum transport through the flow and letting material actually accrete are MHD instabilities, in particular magnetorotational instability. And a natural consequence of that is amplified magnetic fields that will buoyantly rise out of the disk and produce highly magnetized and presumably magnetically heated gas sort of above and below the accretion disk. And fundamentally, that's what's giving us the X-ray emission. Now, just in contrast this morning, I want to put some magnetic field strengths, some typical magnetic field strengths we think about here. So for AGN, the supermassive black hole case, we're typically thinking 10 to the 3 Gauss as being this, the kind of field strengths here. For X-ray binaries, the stellar mass black holes typically 10 to the 7 Gauss. So we're not talking extreme QED. Okay, the physics is boring here, but the astrophysics is interesting. So, okay. So let's quickly run through, just to orient people, the basic physical processes here. So imagine this blob of energized, optically thin plasma above our optically thick, relatively cold accretion disk. The accretion disk is pouring UV optical photons off. So there's some kind of heating that goes on, again, presumably magnetically. There's magnetic fields that are originating from the accretion disk, or at least anchored to the accretion disk, and they're heating the particles in the corona. The main cooling term that we believe is at play in Coronae is Comptonization. So you have the soft photons, which are inverse Compton scattering off the electrons, and also the positrons, of course, and they can inverse Compton scatter multiple times and escape. They can also Compton scatter and then shine back down onto the accretion disk, and can either be reabsorbed in the accretion disk, or they can be, quote, reflected off. You get an X-ray reflection spectrum. It's a magnetized plasma, so there can be cyclosynchrotron radiation that can be made. That can be another source of soft photons that can actually undergo Comptonization. And then, of course, the reason why I'm in this session is there can be pair production and pair annihilation at play. And one of the goals so in the first half of my talk is to convince you that the pair production and pair annihilation may be a critical process in determining the properties of these Coronae. So one of the things you can do, and this is some seminal work in the 90s by Hart and Moraski, you can set up a very simple consideration where you just consider this a two-state system. This is a system A, system B, and then look at the energy connections between them. Look at the energy flows between them. So we have a soft X-ray flux soft photon flux that comes off the disk, optical UV flux LS. That gets Comptonized in the corona, and we introduce a Compton amplification parameter A. And then we have hard emission, hard X-rays, some of which will leave the system, some of which will shine back down onto the disk. We take some fraction eta of the Comptonized emission that shines back down onto the disk. Some of that will be reflected off the disk, some of it's absorbed in the disk. And we can then just impose a steady state on the whole system. We say that the energy, and of course the thing that drives the whole thing is the basic heating term. So we assume that there's some release of gravitational potential, there's some gravitational energy, PG, that's the fundamental power that's fueling the whole thing. Some fraction of that F is heating the corona, and some fraction 1 minus F is heating the disk. That's the fundamental system there. And then you can just impose energy balance, say that heating must equal cooling in the disk, heating must equal cooling in the corona. And you find that because of this coupling that exists between them, especially the fact that the corona is actually heating the disk, some of that's being absorbed and then is part of the emission, the soft emission that is also then comptonized in the corona, that gives you a coupling between the systems. It actually constrains the parameters of the systems quite tightly. So just sort of setting up the two balance equations for that and solving, you can determine that the Compton amplification parameter A is just given by this set of constants here. And you can then relate that through thermal Comptonization theory to the Compton Y parameter, which is basically just optical depth times temperature in dimensionless form. And you find that the fact that this rate of coupling actually constrains A quite tightly, therefore it constrains the Compton Y parameter quite tightly. You can then go on to say, what does that mean for the spectrum? Once you know the Compton Y parameter of the corona, that combination of optical depth and temperature, you can start to predict the spectrum of the corona. And fundamentally, if for photon energies that are well below the temperature of the corona, the spectrum predicts to be a power law. Fundamentally, you're taking your thermal photons and you're just doing 1 scattering, 2 scatterings, 3 scatterings in the corona. After each scattering, there's a probability of escape, of course. And they stack up to be a power law. And it was back in the 70s that Shapiro connected that Compton Y parameter to the spectral slope. So you fold that all through, you can actually predict as a function of the energy dissipation fraction in the corona what the slope of the spectrum should be. The spectral index alpha. The spectrum is e to the minus alpha. And this curve here shows you what that looks like. So for low, if there's a small fraction of energy released in the corona, then the predicted spectrum is actually quite steep. So it's a very, very soft spectrum. And it gets harder and harder as you release more and more energy in the corona, bottoming out something like about 0.8 or so. This is the observed range for AGN. Most AGN have a very well-defined range of spectral indices of X-ray spectra. And so you can see this is pushing you all the way to very high dissipation rates in the corona, or in fact it doesn't work at all. There are observed sources where this just doesn't work. So what does this mean? Well, almost certainly the place where this argument goes wrong for the sources that are so hard that you just can't make it work is the assumption that you've got the accretion disk underlying the entire corona. So in this community, one of the bits of jargon is we talk about photon-starved geometries of the corona. And what that means are geometries where you can Comptonize the emission in the corona, and then it can escape in many directions without hitting the disk. So the photon-starved means that you do that. And another sort of part of that is that there can be many directions out of the disk that don't pass through the corona. That's another version of this. But you break that connection, that strict connection between the coronal emission and the amount of soft emission that reprocesses off the disk. So this was the geometry we were just talking about, so-called sandwich geometry for obvious reasons. But you can have these other geometries which are photon-starved in this sense, and each of them predicts slightly different spectrum. I just put up here one geometry that has become popular amongst certain parts of the field, so-called lamppost geometry, and I'll come back to this in a few slides, where you may have some corona that is hanging on the poles there. What could this be? People have talked about things like failed jets. If you have some kind of Blamp-Posnaic process where you're extracting energy from a spinning black hole, that could give you some energy deposition up there. Not entirely clear what's going on in that lamppost if it's real. Okay, so one constraint on this geometry, just to highlight it, has come from IXPE. We heard about IXPE in the last talk, and there's only a few black hole systems that actually have constrained X-ray polarization. This is one of them, Cygnus X1, the classic first black hole discovered. This is a slightly busy chart from the IXPE paper on this, and it's a bit of an eye chart, so hopefully you've had your eye tests recently, because some of the key interesting things are on these tiny, tiny little insets. But the key thing is here that this system has a jet, and so we can make an assumption, you could question it, but you can make an assumption that jet is lying perpendicular to the disk plane. So if you make that assumption, we now know the direction that the disk plane lies. And it turns out that the polarization angle is aligned along that jet perfectly, okay? Which is telling you something about the polarization, about the geometry of the corona that it's scattering from. So what they do in this paper is to show that, in fact, the sandwich geometry, the one that doesn't work spectrally in many systems, is exactly the one that's working to give you the right polarization signal. Some of these other geometries would predict polarization that's actually 90 degrees round. Now, as Yuri was saying, you know, polarization is a very powerful probe, but you've got to be careful in your interpretation. It doesn't take much of an additional scattering atmosphere, for example. You need to one scattering by every so often to really change the polarization signal. So it's not completely clear that these other geometries are robust, or that rejecting them is robust if you put in, say, another layer of a wind that you're scattering off. But that's, you know, there's some really interesting constraints coming from polarization. Okay, let's get to the main topic, the role of pairs. So again, this has been a topic that's got a long, rich history to it, starting off in the 70s when people were talking about starting to really get their hands on around the question of what happens with relativistic plasmas. I want to pick this story up with Svensson in the 80s, who started looking at mildly relativistic plasmas, which turned out to sort of be the one that's most relevant here. And this plot here, let me unpack this for you. So on the x-axis now we have log theta. Theta is our dimensionless temperature. So it's the temperature scaled into rest mass units of the electron. So a theta of 1 is 511 keV. Z here is the pair fraction. So it's the number density of positrons over the number density of protons. So you can be either very pair-free or very, very pair-rich on this axis. And what Svensson found is that in these settings here, he looks at a situation where he assumed that you had this blob of plasma, it was heated. The only soft photons, it was Comptonized, it was cooling by Comptonization. The only soft photons that were seeded in the Comptonization were produced purely internally through Bremsstrahlung. And he didn't allow anything to escape, so the pair escaped. And then he looked at the pair equilibria that resulted from this. And he found these curves. And there's two interesting things here. One of them is that there is a maximum possible temperature you can be at. If you impose pair equilibrium, you cannot be hotter than a certain amount. Oh, sorry. There's lots of so these are pair equilibria. So this is temperature versus the pair fraction. Follow each curve. That is an equilibrium curve. This number here is the proton optical depth. So if you imagine a corona with a certain number of protons, and for example you start cranking the heat up, you would follow one of these curves. Okay. And so there's a certain maximum temperature you can have. And for a given temperature, in many ranges, there are two possible solutions. There's actually a pair-dominated solution and a pair pore solution, which is interesting. They would differ tremendously by how much heat you're putting in, by how high you have the heating turned up, and they would differ tremendously in their luminosity. But for a given temperature, you can have a pair-free solution and a pair-rich solution. Now let's take this and put it into the context of a corona. And again, there's lots of nice work done here. I've shown the paper by Jim Dove and Wilms and Biegelman from '97, and they adopted the code of Boris Stern, which is a sort of classic nonlinear Monte Carlo code, and they asked the question: you have a corona. They included Comptonization, they included reprocessing of the disk, and they included pair production. What happens as you take a corona and just start cranking the temperature up? And if you look at this inset, this is the line you follow if you take a corona and you just progressively crank up the heating. You crank up the heating, you get hotter, yes, But then there comes a point when you top out and you reach that sort of pair limit, that you reach the limit where pairs are now strongly dominating. The optical depth starts to go up, and that's all the pairs doing that. And as the optical depth goes up, you start to cool your corona back down because of the increased Comptonization of the soft emission. So, and then you can repeat that exercise as a function of your proton optical depth, the floor to your optical depth, and you find that your paths map out a region here. There's a forbidden region here. You know, no matter how much you crank up the heating, you cannot heat a corona of a certain optical depth beyond the limit. So in the community, we talk about a pair thermostat. You know, the pair production is producing a fundamental limit on how hot you can go. The pairs kick in, slap the temperature down once you get too hot. Now, another piece of jargon here, we talk about the radiative compactness of a corona, which fundamentally is the luminosity of the corona divided by the radius, with constants put in to make it dimensionless. And if you expand that out in some interesting terms, so this is the proton-electron mass ratio times the luminosity in Eddington units times 1 over Rg in gravitational units. So it's very easy to see that if you have a black hole and you have a relatively compact corona around a black hole, so R, the radius is of the order of Rg, and you have a system which is close, within a couple of orders of magnitude of the Eddington limit being the maximum where you start to blow away your accretion disk, that coronal compactness can become quite large. That coronal compactness can become 10 to the 2, 10 to the 3 quite readily. Now that's the number that is labeling these curves, and that's the coronal compactness. It's this L here. It turns out that this L is a very useful quantity because we can start to map out the physics on the compactness theta plane. And you can put a lot of the key quantities in terms of this compactness. So, for example, the Compton cooling time of the electron population is given by this expression. So the Compton cooling time is basically the light crossing time multiplied by things of order unity divided by the compactness. So the compactness, order unity of compactness, is the same statement as a electron will cool before it crosses the corona. So it's telling you whether an electron can actually cross the corona before cooling. You can also put some of the key coupling timescales into the compactness language. So on this plot here, the TB equals TC. That's where Bremsstrahlung and Comptonization are trading off. So below here, the internal emission of the corona. The corona is principally cooling by Bremsstrahlung. Above here is cooling by Comptonization. This is the line below which electrons and protons are coupled, and above here they're not coupled on a cooling time. And this is the line where even electron-electron coupling, above that, the electron-electron coupling is slower than the cooling time. And here's the forbidden region for pairs. Okay, so that's a useful. Now, why is this a useful space? This is a useful space because we can make contact with observations on this space, and we can see, what do real systems think about all this theory. So to do that, you have to be able to measure the compactness and the temperature if you want to put real systems on here. So fundamentally, we need to measure the temperature of the corona, measure the luminosity of the corona, which is pretty trivial because you just see how much emission you're getting, and then measure the size of the corona. So firstly, the temperature. Well, this is, general statements made whenever you build a new instrument, you can do interesting things with it. That was true back in 2012 when NuSTAR was launched. So NuSTAR is the first and right now only focusing hard X-ray telescope. So it's a very sensitive, gives you ability to make very sensitive hard X-ray spectra. And this is again one of the first objects for which we could clearly see the thermal rollover of the corona. So if I go back, I meant to point out this is the coronal emission, and this this rollover here is, that time went fast, didn't it? The rollover here is measuring the temperature. So you get this temperature here. So temperatures are easy to measure. What about the size of the corona? The size of the corona You measure, well, it's hard to measure, but one way to do it is actually through timing of the variations of the corona versus the variations in reprocessed emission. And on here, one of the key reprocessed emissions is a so-called X-ray reflection spectrum. You're blasting the surface of the accretion disk with this intense hard X-ray emission. It reprocesses that emission back. You get fluorescent ion lines, you get Compton scattering back. And these are calculations, these particular ones from Javier Garcia, of the kind of reflection spectrum you get back off here. You can see time delays between variations in the corona and variations in the in that spectrum. So this is one particular example. What I want to see here is this is the time lag versus energy in the spectrum, and you can see this feature here. That is the time delayed ion line that's coming from that reflection. So this just gives us a spatial scale, you know, and we can use that to determine the scale of the corona. So you do that, and you put those, you work out the compactness, work out the temperature, put them on the plot, and that's what you get. So you can see that the sources certainly respect the pair exclusion region. They're not hugging right up against it, but then you remember that you're just observing that cutoff and fitting a thermal spectrum, a thermal compensation spectrum to it, and you haven't corrected for gravitational reddening of that. So your gravitational redshift of that source. Correct for gravitational redshift, the corona actually get a little bit hotter in their rest frame, and you get even closer to that line. Okay, so you look at this, and you know, it sure looks like real sources start to respect this line, and are getting very close to it. So that is, you know, we are taking in the community, we're taking that as being pretty good evidence that these corona are actually respecting the pair productions relevant in this corona. Let me briefly say, recently there have been cool coronae found, which are way off this line, and it could just be that nature also, you know, doesn't mind things that are giving you sources that don't have pair production. But another possibility, of course, I'm assuming purely thermal coronae. And it's very reasonable to assume that there's non-thermal components in the non-thermal distributions. And as soon as you have non-thermal distribution, you put them into this picture, then the number of photons that are the number of photon-photon interactions in your pair production can dramatically increase for a given temperature. So if you look at models with increasingly large non-thermal fractions, then you can see that that's really eating into that. You could easily explain cool coronae even within this picture. Okay, let's see. I've got what, 2 minutes left? Let me hit just two highlights then. One is open questions, heating of coronae. I don't have anything to say about this other than just highlighting some really nice work. So this is what I haven't mentioned these simulations so far. I don't think we understand heating of coronae, but there certainly are some nice MHD work that is showing that you've got magnetic fields coming off the accretion disk. You're going to get magnetic heating of the hot gas. This is nice work by Chris Bambick, who's here, and we'll be discussing this later. And you can extend this into GRMHD as well. So these are some models from Julian Krolig's group, seeing heating of coronae in the in GRMHD. The other thing I want to just quickly flag are it's interesting possibilities in non-equilibrium situations. Everything I said now is assumed that you've got this strict balance going on. Well, these are what the light curves of real AGN look like. This corona is not static. It's varying dramatically. It can vary on getting close to light crossing timescales, it seems. So it's certainly equilibrium is not a good assumption probably for these coronae. It is unclear what that means. I would say there hasn't been much theoretical work done on that. And let's skip to this. One of the most interesting aspects for some parts of the community is that you can get QPOs you can get quasi-periodic oscillations from these systems. You get almost periodic light variability from this. This is one AGN 1927 that shows these beautiful oscillations that give you this peak in the power spectrum. In this particular object, it's possible it could be an orbiter. There could be another system in there that's orbiting around giving you this. But in galactic black holes, they show strong QPOs, and it's clearly not an orbiter. One of the things that I just want to, I'll end with this. I found this old suggestion, and I don't know why I didn't know this before, from 91, that QPOs could be limit cycles between pair-free and pair-rich states. And this is an old paper by Kanosi and Minishiga that arguing this. And I think, asking what, with the light of a new understanding of accretionist Coronae, what kind of conditions would you need to be able to get interesting limit cycles that could drive some of this variability would be interesting. I want to flag a poster by Nessa Lopez-Pacurio, who's a postdoc at Maryland. So let me quickly race through to conclusions, put them up, and I'll take questions. Thank you.
Thank you very much, Christopher. All right, we've got time for plenty of discussion and questions.
Thank you, Louise. Thank you very much for such a clear and nice talk. An easy question for you, right? To follow up on the last bullet point.
Yeah.
So what is the story with neutrinos? What's the current status of our understanding of this?
That wasn't a plant, really. Yeah, I mean, this is one of those things that truly caught me by surprise. I wasn't paying attention to the literature because I had other things that occupied me. That there now seems to be a pretty convincing detection of a safer galaxy, NGC 1068, with an ice cube. Would it be something you'd bet the house on? Not quite yet, but it's getting stronger with time. And let me just, I don't want to give a whole other talking, but just to say, the interesting thing here, when you look at those models, is that you have this is now the spectrum of the source, including neutrinos, very strong neutrino signal, yet very weak gamma rays. And you'd have thought, to some degree, the hadronic processes that would give you the mesons and then give you the high energy, the TeV neutrinos, should be generating copious gamma rays. And the way out of this is that you have to absorb those gamma rays in a very photon-rich environment, the corona. So the argument is that there's a very strong argument, I think, that as in all astrophysics is circumstantial, but there's strong circumstantial evidence that these neutrinos may well be coming from a very relativistic proton population that is in the core regions of the corona. You can't even have it uniformly spread through the corona, so you overproduce the gamma rays. It has to be in the core of the corona, so the gamma rays can then be absorbed further out. There's where is it gone? There's these other three that they haven't yet risen to the level of gold standard, but as time goes on, it's a hard business. These neutrinos come in very slowly. So.
Anyone else?
So in the slide that you showed with the pair equilibrium lines, the different geometries and the sources respecting it or not respecting it, if you go back to that. Oh no, there was one with different source, geometries, different geometries. Yes. Oh yeah, maybe that was it. Yeah, no, actually the one before, yeah.
Sorry, this one?
Yeah, that one. I guess it is implying that you have different geometries that have different pair equilibrium lines, right? And
yeah, it's because of the connection with the reprocessor. The corona and disk form this coupled system where some fraction of the coronal emission is shining back down on the disk, being reprocessed back into soft photons, going back into the corona. And so the different geometries are giving you the different levels of reprocessing back into the corona. So that gives you these different lines.
But all these pair equilibrium models assume that the corona has a constant, uniform temperature?
Yes.
The uniform temperature, and that's may or may not be
That
true,
may or may not be
too.
true. Yeah,
Okay.
yeah. I mean, pretty much everything, all these arguments are sort of single zone arguments for the corona.
Or do you want to use the microphone just here? Then I don't have to run around.
Oh, yeah. Thanks, Chris, for the talk. I had one clarification question about, in particular, Cygnus X1 and its two phases. So one thing I have a hard time conceptualizing myself is how do you tie the model of, say, the sandwich Coronae with in two different phases, and especially given how much the luminosity varies in between the two phases.
Yeah, no, good question. So yeah, I didn't talk at all about state changes in these systems. And you're quite right that it may be very hard to reconcile one given coronal geometry with the way these sources can change as they go through different states. And for the non-astro people here, especially we see this quite prominently in stellar accreting mass black holes, that as they cycle through different mass accretion rates, that they can go through outbursts where you have a trickle of matter going onto it and then a flood and then a trickle. As they do that, they can go through some very dramatic changes in their spectrum and their timing properties. And we interpret that as the accretion disk going through some definite state changes. The accretion disk may be changing geometry, going from geometrically thin to geometrically thick states or other such, having truncation radii in them, that kind of thing. It's a complicated phenomenology there. And this may be one of these senses in which the term black hole corona is such a general one. We could use it anything that's quantizing and giving us the hard X-rays. It may be a bit too general to really put into one picture through that.
I guess my question is about the state of the art of both observational and theoretical understanding, whether we think for at least Cygnus X1, which is the clearest of them, is there any constraint on what the corona looks like in one state versus the other and what's preferred?
Cygnus X1 is actually an interesting object because it's a high mass X-ray binary. It goes through, it shows you two states. But in fact, if you take a broad view of it, they don't actually have that different luminosity. It's kind of really a pivoting spectrum. So I would say that I'm not aware of anything that's relatively new on that. There's old arguments that say that it can't be a sandwich geometry in the hard state because the spectrum is just too hard. The Hart-Moravsky argument would kill that. In the soft state, it's a different matter that may well be allowable for a sandwich geometry. The polarization constraints I showed you, though, however, were the hard state. So.
I've got a question. So this is maybe naive, but coming from outside of the astro background, most of the understanding seems to come from the energy balance of the situation. I guess, can you comment on the plasma physics that's maybe taking place? I think you hinted at it with the simulations, but which are the important plasma processes which might then feed back to tell you something?
Yes. I mean, I may not be the best person here. I mean, Sasha may be a lot better on this one, but I would say in terms of the work that's done, a lot of this is coming from the MHD direction. So there's no plasma physics. It's just the fluid dynamics, trying to understand the global energetics of it, the global heating energetics. Then I think handing that off to the plasma models. We're trying to understand partitioning of energy between electrons and protons and some of the acceleration mechanisms. That's where that work is.
And does the ratio of the positrons to protons significantly change the situation or for the plasma physics, or that's not something that's too worrying?
Sasha, do you want to comment on that? Yeah, I think it's still unclear.
Oh. Well, from the experimental point of view, we like it if there's some protons because that's much easier.
Yeah. And certainly from the astrophysics perspective, a really key question is whatever's heating the corona is the heat going into the protons or the electrons,
So
or the
that's,
leptons.
yeah, we can understand the plasma processes within. Okay, great. We've got time for one last question, if anybody's got one.
Along those lines, what is the plasma beta of the accretion?
Good question. So the accretion disk itself is thought to be high beta, and I think it's an excellent question what the beta of the corona is. I don't think we've got any really solid constraints on that. Almost certainly low, but how low is unclear. A lot of the MHD modeling of this, what we find, I mean, there's a lot of gorgeous, giant simulations being done with the GR and the MHD in. One interesting aspect there is that the final outcome of the accretion, of the final outcome of the system, is actually quite strongly dependent upon some initial conditions you assume for the magnetic field. So if there's a lot of net flux in the simulation, you tend to accumulate that flux. You form what's called a magnetically arrested disk, a MAD, and some of the region off of this can be extremely strongly magnetized. But I couldn't put a beta on it for you, but it's very strongly magnetized. The beta it's a little less extreme if there aren't those strong net flux regions.
Great. Well, if there's no more questions, let's thank Christopher again.